All right. Well, let's get back. So, welcome to lecture two. Lecture two? No, lecture three. Lecture three. Sorry. Welcome to lecture three of machine learning two. This is DS 4420, course in Northeastern University, and I'm Professor Wu. So, today we're going to review the concept of maximization and minimization. Hopefully, you learned this already from calculus. When you see something that looks like this, max, some function, what it's saying is that we're trying to find the x such that the function f of x is maximized. That's what that's saying. Conversely, here we're trying to find the x such that f of x is minimized. So these are called optimization problems, where you're trying to find the optimal, the highest or the lowest point of some function. Now, majority of the machine learning algorithms are framed these way, framed like optimization problems. So now, problems we might want to solve might look something like this, right? So this right here is an equation, and you want to find alpha and beta that makes this equation as small, minimized as possible. So ideally, we want to solve this, but just to demonstrate the point, why don't we start off by doing something that's much simpler? With this, we know it's a parabola from algebra, and we also know that when we're trying to find the minimal point, it happens to be zero. So if we know all these already, this allows us to essentially study particular algorithms on how we can find a minimum point. Okay, so the way we could do this to solve this, assuming that we can't just set the derivative to zero, is we can start by just picking some random point, 2. Obviously, 2 is not the minimum, right? We start somewhere, but let's say we start 2. You can essentially start from anywhere. So this function alpha squared will start alpha equals to 2. And when you start at 2, the idea is you want to incrementally step towards the optimal solution. So we want to incrementally start heading towards the optimal solution. So if 2 is where we are now, and we want to subtract some value such that it heads towards the optimal solution, then what should we subtract? Okay. Now, obviously, by looking at this, we want to subtract 2, and you would jump here. But we don't know it's 2. So it turns out that if we just look at the derivative, it tells us exactly which way to go. So remember what I told you. Derivative says that as you x increases, this is going to increase, which also means that as x decreases, it's going to go down. Okay, so if that's a positive, that's what's happening. So by having the derivative information, it essentially tells us what to put in this algorithm. Okay, let's pick a random point, like I just told you, 2, right? Well, if we put 2 into the derivative, remember the derivative is 2 alpha. If we pick 2 in there, then 2 times 2 is 4. So it's telling us that if we subtract 4, it's going to walk towards the right direction, right? Which it did walk towards the correct direction, but it went too far and it overshot the 0th point. So in this particular case, the derivative tells us essentially tells us which way to go. If we plug the derivative information, right? If it's a positive derivative, then it's going to tell us to go left. If it's a negative derivative, like over here, the negative is it's going to tell us to go walk right. So the derivative tells us which way to go, to walk towards the right or walk towards the left. Okay. However, there's a problem that if you walk too far, then you still don't get the solution. So what we could do is instead of walking completely at particular direction, we walk a tiny bit. So we multiply by zero point 0.2. So we're not walking a lot. We're walking a little bit in that direction. If you do this, right? If you do this, instead of walking really, really far, what happens is when you do 4 times zero point 0.2, that becomes uh, zero point 0.8, right? And then 2 minus zero point 0.8 is 1.2. So instead of shooting all the way here, if you were to put the derivative information here, you would start walking towards the right direction incrementally. So once again, the algorithm I'm teaching you of how you can identify the minimum point is to use the current point right now and subtract something. And we're saying that that something, if you put some kind of derivative information in here, because the derivative will tell you which way to go right or left, right? If it's positive, it's telling you to go left. If it's negative, right, negative, it's going to tell you to go right. So we want to put some kind of derivative information because it tells us which way to go, but we don't want to walk too far just in case we overshoot. So we multiply by some constant, and that gives our next location. Once we have the next location, we can repeat the process. By repeating process, we find the derivative again at this point, and then it'll tell us to walk again, walk again, walk again, and eventually we'll reach the 0th point. So this algorithm is one of the most famous algorithms in machine learning, and it's called gradient descent. Now, over this particular example with x squared, right? We know the minimum point must be the point where the derivative is 0. df dx equals to 0, which if the derivative is 2x, then the point where it's 0 has to be 0. So this particular case is easy because we can just take the derivative and set it to 0. But in some cases, you can't just take the derivative and set it to 0. And for those cases, it's very nice for you to end up using gradient descent, where you just randomly pick a point by looking at the derivative, all right? Positive derivative, well, you want to walk towards the left. Over here, positive derivative, you walk towards the left. So you just keep going until you reach the minimum point. So this algorithm is essentially the standard approach to find the minimum of a function, even if the function could be really, really complicated. So this is gradient descent. Now, in case you're wondering, like we started at 2. If we had started here, right? Notice this is a minus derivative at this point, right? Minus means that as you walk, as x increases, the function is going down. Therefore, a minus and a minus is equal to a plus, telling you that if you're at this point, you're going to walk towards the right, right? Minus 2 plus 1, right? That's going to give you, it's going to walk you towards the right. Okay, so this would have happened if you started, regardless of which side you're on. Okay, so knowing how to plot your data. Once you have some kind of data, these are the points. The way you will plot these points is called scatter. Okay, so you want to use the library called matplotlib, and this allows you to plot the scatter. And then you can essentially draw a line. If you want to draw lines, you create all the points you want. So this creates point between 0 and 6 and creates 100 points in between. Once you have x, you can calculate the line, which this particular line is 2 times x plus 1, right? So you calculate line. And you can plot the line by putting the x point and the y points. So the blue line came from here. And the rest of them just basically tells you what the label should be and then plot the plot. All right, so now you want to basically repeat, do what we just did. Let's say we have a function x squared, which is the same as before. Let's say we use the eta 0.1 and we start at a point of 10. Your goal, your first assignment, is to see whether you can write this very simple algorithm. I'm going to write this very simple algorithm, gradient descent, and run it in a loop, like I don't know, 20 times or something, or 100 times, and see if you will get close to zero. Because we know the solution is zero, right? So now, yeah, pause the video, see if you can do it. I have written the code myself for you. You can see that I basically run it in a loop where the next location is the current location subtract by the derivative. And then I just keep putting the current location into the derivative. And then what I do is I keep printing out the current x value. You can see that I started from 10 and the x value keeps decreasing. Right? It heads towards zero. Right? So this is the solution, and this is what I'm heading towards. Okay. So you should, when you run this, you should get the same solution. All right. So that was with one dimension. We have previously learned how to do it in higher dimension, right? When we have a higher dimension, in those cases, it's not just one, right? In the previous gradient descent, pretend it is just like one line. But when we have multiple dimensions, then we need the derivative with respect to each variable. And since there are two variables here, alpha and beta, we then need to break up each dimension. So when you run gradient descent, you essentially look at all alpha next is equal to alpha now, subtract the gradient information at the alpha and beta now. Okay. So let's see if we can do this for the next exercise. Take out a piece of paper, see if you can take one step. Okay. Let's say you see if you can take the derivative with respect to alpha and beta, which you should get this. And then given the step size as zero point 0.2, and we start at 1 and 2. Okay, so give this a try. All right, I wrote the solution out for you here. So once you tried it, you can check out the solution yourself. Okay, so next part. With machine learning, right, there are many, many paradigms, learning paradigms. There are supervised learning, unsupervised learning, semi-supervised. I mean, the list goes on. It's a pretty big list. One of the most common, when you think of machine learning, the first thing you think of tends to be supervised learning. In supervised learning, what happened is you have some kind of data, and the data is able to predict some kind of label. Right? So, for example, you might want to look at the for housing price, you want to look at the square footage of the house, you want to look at how many bedrooms, the bathroom, the quality, and from that we might be able to predict the label, which is the price of the apartment. Right? So, and another thing like stocks, right? You could have the stock market data of the last month, and you want to predict the stock price tomorrow, for example. So all these things are called supervised learning, where it allows you to predict what is going to happen or what the machine should do. Okay. Now, with supervised learning, it's then divided into two types. One is called regression, other is called classification. Well, regression, remember, we have labels. You're trying to predict the label. So, regression, you're trying to predict continuous labels. Time, right? Time is a continuous thing. Like, and then, and then classification is when you're trying to predict categories. So, let's say you have like the number of bedrooms, right? You're not going to have one and a half bedroom. It's just one, two, three, four. Or you want to do item recognition. You want to recognize whether this is a glasses or is this a cat, for example. So these are there's no half a glasses and half a cat kind of thing. So these are very discrete. So your label can either be continuous or discrete. Like height is one, Boston housing price, weight, how long a person lives, right? All these are continuous. And for this class, we're going to start by really focusing on regression and later on move on to classification. And of course, we'll also do some unsupervised supervised. So if supervised means you're trying to predict some kind of label, right? Like regression or classification. Unsupervised means there are no labels. You want to see if you can generate the label. So these are two types of problems that we'll probably look at. Okay, so regression. The idea of regression is very simple. We have some kind of data, we'll call it X. What we want to do is put this data into some kind of function, and then it will give us some kind of predictive label. So this is predicted label, predicted. And then we want our prediction to be as close to the true label as possible, right? We want whatever we predict and the true outcome to be exactly the same. So therefore, the idea of regression is that you want the distance, some kind of distance between your prediction and the truth to be minimized. Okay, you want to find the function. So another way you can write it is you want to find a function such that the distance between all the points and the label to be as small as possible. That's the idea of regression, right? You're doing an optimization problem where your goal is to find this function. So right here, this right here is how you should understand the concept of regression. And well, this is the most common way to do it. There's a different way to do it, but here's your function. You want to find the function such that your uh, output of your function and the actual label itself to be as small as possible. And the way you do it, one of the distance they use is called the Euclidean distance, right? And with the Euclidean distance, for every single point from one to n points, what you can do is you want this minus this to be as small as possible. So if your prediction and this and the truth is the same, then their distance will be zero. So you can view this as a distance, or you can view this as some kind of error. So you're trying to you're trying to find a function that minimizes the average error, right? You basically sum up all the error divided by n. And they like to do average error square so that like positive error or negative error are treated the same way, right? Because um, if this is greater than this or this is greater than this, that will either give you a positive or negative value that could potentially cancel each other out. But if you square them, then it's always a positive value. So whenever there's any difference, you're just trying to minimize that. And this objective is the most common objective called the mean square error. Okay, so this is the mean square error. The error, you can see the mean means the average, so it's the average square. So this is the error. So this is the error square, right? So this average square of the error. Okay, so how do we find the best function? Well, finding this function is really, really hard, right? If you don't have any guidance. So so what we normally do is that instead of knowing what this function is, we make the assumption that this function is some kind of combination of other functions. So a linear combination. So this function is a combination of phi 1, phi 2, phi 3, so on. Okay. So this is like this is an assumption. It's not necessarily true. And therefore, depending on the assumption you make, you can have a very good function or you can have a very bad function. So this is by by picking ahead of time. So what we do is we ahead of time pick these functions. And then what we do is we find the weight. So the combination of these functions. How much weight should we put in this function? Right? Maybe we want to put a zero because this function doesn't help us. Maybe we want to put a large number here. So it's a combination, weighted combination of the functions. Okay. So once again, our goal is that we want to find the function such that the distance between the prediction of our function and the actual label itself are as small as possible. And since it's really hard to find the function, we simply assume that the function is a combination of other functions, phi 1, phi 2, phi 3, right? So all we have to do, we already assume these functions, so we know them. What we're trying to find is W1, W2, W3. And that drastically simplifies the problem. So the function we pick, right? The function we pick as a combination, they're called basis functions. So these ones, they're called basis functions. And the constants that we're trying to find, W1, W2, W3, they're called the weights. So we set the basis function as the basis of assumption. Once we have the basis, for assume, then we find the weights. So the weights basically tell us how much of each function we should incorporate into the final. So by representing the final function as a combination of other functions, we really simplify the objective. So over here, this is not easy, right? We don't know how to pick a function. But now, if we pick a bunch of functions, we're not sure which one is good, but we simply find the weight. And the weight tells us how important each one is. Now, this is a much easier function. Okay? So, the weight right here is a vector. Now, remember, we wrote it this way, right? But if you go back to your linear algebra, this is also equal to W1, W2, W3, so on and so forth. Phi 1, phi 2, phi 3, so on and so forth. Notice how if you just multiply them together, it gives you the same equation. And we're going to call this right here, instead of W1, W2, W3, we're just going to call it W. So that represents this entire vector. And this right here, I'm just going to call it phi of x. So, so that's how we got this point to here. Right? Instead of a function, it is now phi of x times w transpose. Now remember what I said the phi of x is and w. So when you multiply them together, we make the assumption that's approximately equal to this. Now, this function here, right, which is a vector of other functions, is called a feature map. Unfortunately, the vector as the result of the feature map is also a feature map. So this is a feature map, and the final result is also a feature map. Okay, so now that we get the basic idea, right? The idea is we instead of a function, we let the function be a combination of other functions. But the question comes, how do we pick these functions? How do we pick each one of these? Well, throughout history, there are some standard ones that people just start picking. One of the easiest one and the very first one that people pick is called a linear function, where you simply let phi 1 equals to x. So any number you put in here, the same number is the output. Like it doesn't get simpler than that. Or maybe it does. And the second function Any number you put in, it's always going to return 1. So this right here is the it's called a linear function. This is one of the earliest and the simplest one you pick. When in doubt in science, they tend to just pick this one because it's really, really easy. Hmm? Therefore, instead of phi 1, phi 2, phi 3, phi 4, there are only two functions, phi 1, phi 2. And you're simply trying to find two numbers, W1, W2. Once you know W1, W2, that essentially gives you a good idea. Now, if we put phi 1 and phi 2 into the function, now, then this is phi 1. Phi 2, remember, is just 1, right? Therefore, we're saying that the equation, the f of x, looks something like this. Or we can pull it out, W1, W2, x and 1. So when we multiply them down, it's equal to this. And of course, we'd like to write things compactly, so we just write W transpose phi of x. Therefore, we can solve for W vector by minimizing this. Okay? And this right here is called a linear regression when we pick these. When you hear about linear regression, like that's what's happening. You are trying to find a function that gives you the output that you desire. You want them to be different. And you happen to be picking the function where where phi 1 phi 2 is equal to x and 1. Now, linear regression is one of them. Another one is called polynomial based function. So the simplest one for polynomial is the second order. In this particular case, you instead of phi 1 phi 2, it has one extra one. It's slightly more complicated, where phi 1 is equal to x squared. Phi 2 is just equal to x. Phi 3 is equal to 1. So if you pick a different basis, now you have a different algorithm called a polynomial. If we put all the individual phi i's into the main function, we see that the equation is identical. So notice how even though we have three of them, right, then this becomes W1, W2, W3. This right here is x squared x, but we write exactly the same thing as linear regression, right? This here, it doesn't care how big the vector W is. You can always write it this way. Always write it this way. Hmm? So here, notice that it doesn't matter what function you pick, right? You can always write it this way. So, but if you happen to pick these as the basis functions, then what you end up solving is this thing called second order polynomial regression. Okay, so linear regression and polynomial regression are the two easiest and the most commonly used basis functions. So just by picking those basis functions, then you have it. Now, remember that the gradient descent algorithm is this, right? So we went over gradient descent today, where whatever we're trying to solve, here's the current one, and here's the next one. And we got to subtract the gradient from it. So since the function we're trying to minimize is this, we're trying to make this as small as possible. So let's take the derivative of this. Well, if we take the derivative of this, then what is this? Right here. We take the derivative, 2 goes down. So 2 goes over 2. And then this part is phi xi transpose w minus yi. And now we need to take the derivative of what's inside with respect to w. And then that's just phi xi. And that's it. That's it. This right here is it. So we now know how to take the derivative. So if we know the derivative, we can essentially pick any point. Like we can pick any point w as a starting point. And then we can just iteratively, right? Iteratively get the next point, and then the next point, and then the next point. And eventually we'll find a w that makes this error, makes the average error, mean square error, as small as possible. Okay? So when that happens, then we essentially find the ideal weight that makes this error as small as possible. And now, so now you know how to find the derivative. If we have time later, I'll go over an easier way to calculate this. But for now, the idea is really simple. You want to run you okay. The idea is really simple. This is the error. You want to find the W that makes the error, your prediction error of your function, and the actual label as small as possible. You want to minimize it. Well, we just learned how to do minimization using gradient descent. By using gradient descent, we start by plugging in some random number, any number we want. Once you plug it in, we 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 crank through the algorithm and then subtract the gradient from it. And every time we subtract the gradient, if you remember, we walk a step closer, a little bit closer, until you eventually reach the minimum point. Okay. So for today, I want you to assume over here is the input, over here is the label. So these are all the possible points, and your goal is to find a line that give you the least amount of error. So these are the points, right? So if you get this correctly, you should get something like this, a line that looks like this, because this minimizes the error. Okay? So So you want to write the code with gradient descent. See if you can obtain this. And then after that, you want to write the code with gradient descent again, but this time use a polynomial, which is a parabola, right? So the polynomial, remember, phi 1 is equal to x squared, phi 2 is equal to x, phi 3 is equal to 1. So, and this one, so it's phi 1 x is equal to x, 2 x is equal to 1. So let's spend some time. This is your next exercise, and we're going to go on. I think we have time, so I'm going to continue. So over here, we calculate the gradient. So notice this requires you that you essentially to have some kind of summation, right? You need to basically take every single point, plug into the basis function, and then subtract this distance, subtract from the actual label, and then multiply. So this right here is not easy to calculate. There's a second way to calculate this, and it's easier to calculate in Python. It's that you simply need to convert them into matrix format. So compact derivative. Okay, so I already told you, we learned that this is phi. And if you have phi here, this means that you have phi 1, phi 2, all the way down, right? These are the basis functions. And this is the compact representation, right? And then once you have phi of x, which is the feature map, you can then start plugging in numbers. You can plug the first sample x1, you can plug the second all the way to xn. Now, you need to notice the difference. Over here, the subscript is in the phi. These are the basis functions, and this is the feature map. Over here, the subscript is at the we're using the feature map, and we're plugging in different samples, Okay, so when we plug x1 here, it's x1 for all the bases. We plug x2, it's x2 for all the bases. Okay, now when we have a lot of samples, we can stack the samples together. So what do? We stack them. This right here is, remember, we stack them horizontally. We stack this from the first sample, this from the second sample. Okay, so when we take the feature map, instead of just one sample, we take the feature map of the entire data. That means we take each sample and pass it through the feature map. Okay? So when we start stacking them this way, we call this matrix capital phi or 5. Okay, so this right here, remember this by definition is the first basis x1, second basis x1, third basis. And over here is the first basis but x2, second basis. So this right here is a matrix where you stack the every single sample together. And that's equal to this matrix right here. Okay, so this right here is for the entire data. Now, how does this help us simplify the calculation of derivatives? Well, remember this is how the derivatives were previously calculated, which requires you to do a bunch of sums. Okay, now let's look at this again. So this right here is the derivative we just calculated. Now, if we have the derivative we just calculated, then um, what the sum is telling us is that we put sum into the i's. So it's x1, y1, x1, x2, y2, x2, right? So it's a summation of all these. That's what the sum is saying. Okay, well, we can find some patterns here. I'm going to call AI equals to this thing here, right? This right here. So this would be called A1. This would be called A2. This would be called A3. So it'd be A1 times 5x1, A2 times 5x2 by setting AI to equal to this. Okay, so this simplifies things. This simplifies things because now we have A1, A2, A3, A4. So after we can look at it this way, we can split them. Notice how we can turn them into a vector product where we have v1, x 5x1, 5x2, x3, and we have the a1 here. So this right here times this is equal to this. Okay? Well, now what is a1 again? Well, we substitute them back in. So a1 is this whole thing. A2 is this whole thing. So that's how we got this part because we substitute each a its definition back in. Well, once we substitute this back in, then we can actually uh, pull out W. So this is the same W. So it's W times this one, then W times this one, then W times this one. And we can pull out the addition. So it's this times this, then subtract Y1. This time this times this, then subtract Y2. So this and this are the identical expression. Now, I just showed you previously. We just talked about how I define phi, which is phi x1, phi x2. So notice what we end up here is this is simply phi, and this is phi transpose. So this right here is how we got phi transpose phi times w, and we're just going to call this entire vector y. Now, this is easy because this is just a bunch of matrix multiplication. You have w times phi, that's a matrix, subtract by 1, that's a vector subtraction, and multiply by w. So this right here is identical to this right here. So you can calculate derivative this way, which then you got to put a lot of things into a loop, right? You got to loop this through every single sample. Or you can calculate this way, which is just a bunch of matrix multiplication. Hmm? Don't look at Drew. Yeah. So if you feel free later on when you're solving this problem to try it both ways. Try it with both derivatives. And you will notice that the code for the compact derivative is much, much shorter. Right? You don't have to put things in loops. So you want to try it with both. Okay, so I think that's it for today's class. I will see you guys next time.